All right, so new problem. That's similar. So suppose there are 200 million people in the United States. Suppose that 100 million are Democrats and 100 million are Republicans. If you draw two people at random, what's the probability that both are Republicans? So I want to find the probability of getting a Republican followed by a Republican. So on your first draw, there are 100 million ways for success. There are 100 million Republicans out of 200 million total possible outcomes. There are 200 million people. So this right here is the probability of getting a Republican on the first draw. Okay, now I want to know, but what's the probability of getting a Republican and then a Republican again? All right, if you got a Republican on the first draw, there are 99,999,999 Republicans left out of 199,999,999 people left. So that number is Republicans left. And that number is the total number of people left. So if you multiply these two fractions, this guy multiplied by this guy, you get about 0.24, let's see, followed by 6 nines, followed by 2 eights. So if you multiply these two fractions, you get about 0.2499999988. Okay, well, so the problem that we just did, well, this problem is really no different than the drawing fruit from the bag problem. The probability of the second draw depends on the outcome of the first draw. The events are dependent. However, because there are so many people in the United States, the probability of getting a Republican on the second draw is still roughly 1/2, regardless of what happened on the first draw. So if we simplify the problem by pretending that the results are independent when they aren't, so if we just pretend like the second draw doesn't depend on the first, like if we pretend like we just took that Republican and threw him back into the mix, and that after we drew the Republican on the first draw, we threw him back into the total population, and so there were still 100 Republicans left out of 200 million people. If we did that, we can estimate the probability in a much easier fashion. So if we just pretend like the draws were independent, we could say, well, the probability of getting a Republican followed by a Republican, we could say, well, it's approximately 1/2 times 1/2, which is 1/4, or in other words, 0.25. So if we pretend like the probability of getting a Republican didn't change on the second draw, we would have estimated our probability to be 0.25, and that is darn close to the actual answer. So when selecting things from a population, it is often helpful to use the following rule. So we got to talk about, well, when is it okay to do this? When can we just estimate a probability rather than finding the exact value? When is the estimate going to be so good that we might as well just multiply probabilities and pretend like the probabilities aren't changing? So when can we do this? Well, your book gives you the following criteria. The 5% guideline for cumbersome calculations. So, all right. If calculating a probability is rather difficult, And if the sample is no more than 5% of the population, treat the selections as being independent, even if the selections are made without replacement, so they are technically dependent. So when we did this estimate here, we use the 5% guideline. If we select 2 people out of 200 million, that's certainly less than 5% of all people, so we can use the 5% guideline to simplify our work. So if you're taking 2 people out of 200 million, yeah, that's less than 5% of the population, so we just use the 5% guideline and just estimate the probability instead. And that estimate is darn good. So, all right. Let's combine some of the concepts that we have learned so far to answer the following problems. So, if a couple has 2 kids, what's the probability that they end up with 2 boys? Now we can think of a couple ways to do this. Okay, option 1, you could do a tree diagram. You could say, okay, they could have a boy for their first child, or they could have a girl. If they have a boy for their first child, they could get a boy for their second child. If they have a boy for their first child, they could then get a girl for their second child. All right, if they have a girl for their first child, they could have a boy for their second child. If they have a girl for their first child, they could have a girl for their second child. So I say, what's the probability that they end up with 2 boys? Well, there's one way to end up with 2 boys out of 4 possible things that could happen. So the probability is 1/4. All right, but yet another way to do this problem would be to say, okay, what's the probability of getting boy and then a boy? Well, these events are independent. It doesn't matter what you have for your first kid. If you have a kid and then you have another kid, the probability of getting a boy for your second kid is still 1/2. So these events are independent. So we could just say, well, 1/2 times 1/2 is 1/4. Probability of boy times the probability of boy is 1/4. Okay. So let's do this problem. If a couple has 2 kids, what's the probability that they end up with at least 1 girl? So in other words, 1 or more girls. Well, okay, we could do this with a tree diagram. We could say that there are 1, 2, 3 ways they could end up with at least 1 girl. So there are 3 ways for success out of 4 total outcomes. So the probability of getting at least 1 girl is 3/4. Okay, but here's another sneaky way to do this problem. So let A be the event at least 1 girl. So call that A. Now, let's think about what a complement is, or in other words, not A. A complement means not having at least 1 girl. But another way of saying not having at least 1 girl is to say having all boys. Okay, now remember, the probability of A plus the probability of not A has to add to 1. Well, we want the probability of A, so we do a little algebra. Subtract probability of not A from both sides. The probability of A, the probability of having at least 1 girl, it's 1 minus the probability of not A. Or in other words, it's 1 minus the probability of having all boys. We found the probability of having all boys in the last problem. It's 1/4. So you could do 1 minus 1/4. And if you do that, you get 3/4. So that's another way to do this problem. To find the probability of at least 1 girl, you could do 1 minus the probability of not at least one girl. In other words, 1 minus the probability of all boys.